Neurons use changes in their membrane potential as ways to communicate, to give and receive signals. And these signals come in two types, graded potentials and action potentials. So a graded potential is a short-lived localized change in the membrane potential. All right, it's a short-lived localized change in the membrane potential. These changes can either be depolarizations or hyperpolarizations. So a depolarization, remember, is when the membrane is being increased in its potential. So if that -70 is resting and it is getting more positive, it's being depolarized. If that polarized membrane is getting more negative, so lower than -70, then it's getting hyperpolarized, like superpolarized. Okay? These graded potentials only occur at the synapse. Okay? And they are mediated by chemical gates. So that means that it's going to require a neurotransmitter to bind to chemical gated channels in order to cause the change in the membrane potential there. All right, so if we look at a synapse, so let's just draw a synapse here. Okay, looking at this right here, this right here is an axon. That means this is the axon terminal. And we call this the presynaptic neuron. So this neuron over here is the postsynaptic neuron. So this whole thing together is a synapse. Okay, you can see here, it's just like at the neuromuscular junction, the axon terminal doesn't touch this neuron over here. There's a space here called the synaptic cleft. Okay, so that's what we're showing here. This looks like the neuromuscular junction. And the neuromuscular junction is an example of a synapse. So inside the terminal, you will find vesicles with neurotransmitter in them, just like in the neuromuscular junction. This is completely the same. So there's neurotransmitter in here, and it could be acetylcholine, but there's a ton of different neurotransmitters, so it could be another kind as well. You'll also see or find special voltage-gated channels at the axon terminal that are specific to calcium. And when an action potential comes down here, it's going to open those gates because they're voltage-gated. And when that happens, calcium is going to come in to the terminal. Just like in the neuromuscular junction, that's going to cause these vesicles to go through exocytosis. And when that happens, their neurotransmitter is going to be barfed out into that cleft. Totally the same. You should know this. On the postsynaptic membrane, you're going to find channels that are gated, and they're chemically gated channels, and they'll have receptor sites for this neurotransmitter. So the neurotransmitter is going to come over and it's going to bind to these things. Again, this is review. This is the same thing that happened at the neuromuscular junction. Those channels are going to open, and sodium is going to come in, flow into the cell, and potassium is going to go out of both channels, like both of all the channels. Both sodium and potassium go out both of channels. One's going in and one's going out. We know from looking at the neuromuscular junction that more sodium will come in because there's a higher gradient for sodium. And when that happens, if you remember, that created the end plate potential, because this is at the end plate. The same thing is going to happen here. This just isn't a muscle cell. So this area here, where the sodium is coming in with all these gates, is going to change the potential here. So it's going to come in quickly at the channel itself, and then as it moves and spreads out, and this is going to spread and spread, and as it does that, it's going to dissipate. Okay, so this area here, due to the sodium coming in, is going to be depolarized, meaning it's just going to get more positive. We don't know how much. Graded potentials are, again, they vary. They're variable, so they vary in strength. So we don't know what this number is. We just know that it's higher than -70 here. Okay? So that is what we call a graded potential. So this depolarization is a graded potential. So the end plate potential was an example of a graded potential. So the strength of that graded potential is going to depend on how much sodium comes in. So ultimately, that's going to depend on how much neurotransmitter comes across, and how much neurotransmitter is going to bind here, and how many of those gates are going to open. Okay, so the more sodium we have coming in here, the stronger this potential is going to be. Okay, and it's, again, going to dissipate as it moves this way. Okay, it's kind of like when you throw a rock into a still pond, and the waves at the beginning are really high, and then they ripple out and get smaller and smaller and smaller until they go away. It's the same thing. Or the same idea, anyway. Okay, so that is a graded potential. So who cares? What do we care about a graded potential for? Well, graded potentials trigger action potentials. So they're kind of important. The end plate potential triggered an action potential along the circle lemma. Okay, it was a graded potential and it triggered an action potential. And that's what graded potentials are going to do. So what's going to happen, and let me make some room for myself here. Whoops. I can draw a little picture here. Okay, so what's going to happen is that we have this neuron here, and it's going to this neuron here, and it's going to create synapses where the axon terminals from this first neuron are. They're going to have synapses here, and they're going to create graded potentials along the cell body of this neuron. And those graded potentials are going to find their way, move down towards the axon hillock of this neuron. If those graded potentials are high enough, or if that graded potential is strong enough, it will trigger an action potential down this neuron. So that is the purpose of the graded potential. So let's talk a little bit about action potentials.